not from your text, but you have to. So here's our gene, here's start site +1, there's the top box. We're only looking at the top box, which determines and aligns the binding of this thing. The protein that eukaryotes it recognizes is called TBP, the top binding protein, which is this darker green part there. TBP is part of this complex that's called the transcription factor 2D. Transcription factor 2D, including TBP, has about 15 proteins there. And it's that factor that recognizes and binds to the tau box. The tau binding protein is the first guy that does it. That factor binds. Once it does, once it binds, there are two other factors that come in: TF2A and TF2B. TF2A actually binds to this guy. You can see it interacting with the green guy there. And then it recruits TF2B. TF2A stabilizes this complex. It stabilizes, helps to stabilize. You can see it's also over the DNA. They recognize DNA in these regions, but it stabilizes the binding of this growing transcription complex. You with me? Once these three bind, then they recruit polymerase. And polymerase is in the nucleus, but not attached to DNA. And it has a transcription factor associated with it called TF2F. And this transcription factor, along with TE, are recognized by this. So TF2F is recognized by TF2E. This guy is recognized by this. So these two together recruit the polymerase to the growing transcription complex. And the next slide is the TF2H. Oops. Okay, so these guys are recruited to this complex here, and when they form a transcription complex that will then copy the DNA make RNA. In order for these guys to bind, once they bind to the sequence here, right, to the promoter region, they make a small piece of RNA, and once again they stop, and they have to release. And there's something. The thing that releases them, or causes them to release, is this factor called TF2H. TF2H has a helicase which opens once this complex binds and forms that first bubble, that transcription bubble, opens the DNA strand, so the helicase helps. But it also has a kinase activity. And the kinase is able to phosphorylate this region, this little thing here, which is called the CTD, right? Which is the CTD, but it's the terminal domain of this polymerase. But I'll tell you. So this is part of the subunit that actually transcribes. This guy's polymerase, carboxy terminal domain, so it's on the carboxy terminal end of the polymerase protein, the capital subunit. Right? And this carboxy terminal domain is a repeat. There's 7 amino acids. It's a heptad. It's repeated many, many, many times. It's repeated 50 times or something. So there's lots of those heptads there. If you look at that heptad repeat, there are 3 amino acids that contain hydroxylates, 2 serines and a threonine. And those serines and threonines can be phosphorylated by this TF2H, right? This transcription factor, this kinase. This is a serine-threonine kinase. It phosphorylates the serines and threonines in this tail region, which is this repeat region that has a lot in there. Still with me? When these are phosphorylated, right, it changes the conformation of this tail region tremendously, and it causes this whole polymerase complex to lose its affinity for these transcription factors that have identified the promoter region. And when it does, when it loses its affinity, the polymerase essentially lets loose of these and continues on in the elongation stage. So, in order to begin transcription, you need these transcription factors to recognize the promoter. When they do, they recruit the polymerase. There's other transcription factors that help to recruit it to this. Once it's recruited there, and the helicase opens up the bubble, then the kinase phosphorylates the tail so that this thing can release and move down and transcribe in the elongation. Does anybody That's the sequence. This is the sequence in yeast, right? So there's a tyrosine, serine, phenylalanine, or proline, tryptophan, serine, proline, set here. So those are the serines and threonines that can be hydroxylated. 3 of them are phosphorylated. 3 of them are hydroxylated on those guys. Yes.
So which T2 or TF2 factors are released? Is it B, A, D, and what else is released?
What are they used for?
No, when are they, which, if all of them, which ones are released?
What happens actually, it's a good question. When this is phosphorylated and it releases, they come, most of these come off. The only one that stays there is this guy like this. He stays there. And what that does is it increases the second round of transcription rate. Right? So the process of this binding takes a certain amount of time. When this guy moves on, elongates, this guy stays there, so it shortens the time to initiate the second round of transcription. That was what that is?
Yeah, then the blue, the polymerase just goes off and leaves TF2.
The polymerase just moves up the DNA.
Okay.
This one stays on that site, so that now the others will start to reinitiate, start a second round. Yes?
I assume once the proteins that are being coded for this region have accumulated to the point where they can fix whatever needs to be fixed, then the TFGD comes off.
I'm not sure. Oh, then this,
Yeah,
when you
like
stop there.
Yeah.
That part, yes, it's a little more complex, but yes. You carry out some very complex, and we're doing this pretty quick. Okay, the one thing I wanted to show you, and we talked about this before when we talked about replication, this diagram represents the histone. Remember, the DNA in eukaryotic cells is wrapped around this histone core. So this core here actually has 8 molecules. There's 2 copies each of the 4 histones, H2A, H2B, H3, and H4. Right? They form what we call a nucleus. So this thing in the middle is a nucleosome. Right? And DNA wraps around that nucleosome. It goes around about twice. It's about 120 nucleotides wrapped around that core. More importantly, what I wanted to show you is that these beads on the string here represent the tails of the histones. So the histones are in that core, but their tails hang out kind of loose. They're out to the side like this, right? And what you can't tell there. The tails of the histone, I'm surprised they don't have it. They have, I'll show you how it's coded in a minute. But the tails of these histones are arginine and lysine rich. So they have lots of arginines and lysine residues. In fact, all of these that are here are arginines and lysines. You can see that they're numbered, so it's not every amino acid. This is amino acid 1, 3, 5, 8, 12, and 16, and so forth. So every one of the ones that are numbered here are either a lysine or an arginine. Now these residues, these tails on these histone molecules can be modified. Lysines and arginines carry charge, so they can be covalently bound. In particular, you can see that these pink guys here, this K is a lysine, right? And the AC is a cell, or it's an acetyl group. So what's happened is that these lysines have been acetylated. Also, these white guys are arginines. Arginines can be methylated, so that's a methyl arginine. The blue guys are lysines that can be also methylated, put a methyl on, right? And these guys here, right, are serines that are phosphorylated. So these guys are serines because they get phosphorylated. So the bottom line on this cartoon is that the tails contain amino acids that can be modified. And the modifications of those tails tremendously changes the behavior of this particular thing called a nucleosome. Okay? So normally, lysine residues, if these were not modified, if they were just lysine, is lysine a charged amino acid? It is a charged amino acid. It's a basic amino acid, which means it carries what charge? It's a positive charge associated with it, right? What about this DNA that's wrapping around? Is DNA charged? Why is it charged? The sugar phosphate backbone, so the phosphates are negatively charged. These lysine residues are positively charged, so they interact very tightly. so that keeps this DNA wrapped very tightly around the nucleosome. And when the DNA is wrapped around the nucleosome like that, enzymes have very little access to it. DNA polymerase, RNA polymerase, they can't get to it. In fact, if you take this nucleosome like this, with that DNA tight, and you put DNase in there, the DNase can't get to the DNA nucleosome. If you take those lysine residues and you acetylate them, what happens to that charge? It's neutralized, right? So if you acetylate these lysine residues, it becomes neutralized, they don't interact with the DNA, it loosens it up. These residues here, there's been a lot of studies on these different, on the different histones here, and these modifications, these acetylations here, are characteristic of DNA that's being transcribed. So one of the things about DNA being transcribed is polymerase having access, right? Polymerase has to find a promoter, what we talk about. But also the DNA has to be modified so that that enzyme is able to work on that DNA. It has to loosen it up. And it's loosened up by modifying these histones.